Now that you've learned about reversible reactions that can reach equilibrium, I want to talk to you about how we can change that equilibrium. First of all, a little bit of review. Some reactions are irreversible and happen only in one direction. You can't go backwards. We can't unburn this piece of paper or unfry an egg. Once that reaction has happened, it is finished. But many other reactions are reversible. Interestingly, many of these reversible reactions are ones that are essential for life, and that's what keeps us going. For example, the picture that I have here is what happens to carbon dioxide. You know, it is produced in body cells, and we have to get rid of it. We have to move it out of the body. And so it's going to move into the bloodstream. And it actually isn't carried as carbon dioxide. It is put into a bicarbonate ion, which is HCO3 -1. And so it is the chemical reaction happens between the carbon dioxide and water to produce this bicarbonate ion. That ion carries it through the blood until we get to the lungs, which is our second picture down here, where the reaction happens in the reverse direction, and we end up with carbon dioxide again being produced as a product, and it leaves the body out through the lungs. And so this is an example of a reversible reaction that's very, very important for us to stay alive. In chemical equilibrium, we have this situation between reactants and products. You start off perhaps with only reactants, and as the reaction occurs, we are moving to products. In this second situation, this is a reaction that favors the production of products, because you can see we have a lot more products over here when we're done. In this third example, the reaction now is more favoring of the reactants. We have more reactants piling up than we have products. And then eventually we'll reach a point where things are at equilibrium, where we see this double arrow showing that there's both a forward reaction happening and a reverse reaction happening. And at this point, the concentration of the reactants and the products is not going to change, but the reaction is actually still going on. We just can't see it. It's kind of like running on a treadmill. In this point of equilibrium, the rates, how fast things are changing of both forward and the reverse reaction are equal. So the amount of product that is being made, reactants going to products, is exactly the same as the amount of product that's turning back into reactant. So the end result is that the concentration does not change. If we're measuring the amount, then we don't see a change in the number, but both reactions are still occurring. And so it's like running on a treadmill. The treadmill is moving, the feet are moving, but the person is not going anywhere, and they are at equilibrium. In the reaction that we did using the simulation on equilibrium, or on reversible reactions, we did see equilibrium be established in our second example. So in our trial number 2, if you look at the numbers, right about 140 seconds, we really kind of see the same numbers showing up again and again. The concentration settled in with about 44 molecules or particles of substance A and 56 of substance B. It kind of fluctuates around that number, but it really doesn't change significantly, whereas our other 2 trials we were still having quite a bit of change going on. So this graph kind of illustrates what happens. After a certain point, we get to a flat line. There's no change in concentration happening. But you remember from that simulation, those molecule particles were still bouncing around. They still were changing color as they went from one side of the reaction to the other. So the reaction was still happening both in the forward and the reverse direction, but we weren't seeing a change in the numbers. So, of course, there's some math involved in this, and we can create something called the equilibrium constant, which is the ratio or a fraction that puts the concentration of the products as compared to the concentration of the reactants. So the products would be written over the reactants. So here's my fraction with just a little slash to indicate the fraction bar. And so if you think about it, here's a graph that illustrates this. Our products are the red line, and so at equilibrium they will be higher on the concentration level than the reactants. So this is the graph that shows a situation where we have more products being produced at that point of equilibrium. There's more products, concentration of products is higher than the concentration of the reactants. So you think about how math works, that'll put a bigger number in the numerator than in the denominator. And so if we did the math, our equilibrium constant would be greater than 1. So if the equilibrium constant is greater than 1, the reactant favors the products. We have more products than reactants when we're at equilibrium. The opposite is true, again, because it's math. If the bigger number is in the denominator, you have a number that's smaller than 1, so your equilibrium constant is less than 1, and the reactant then is the reaction is favoring the reactants. When it reaches equilibrium, when the concentration is not changing anymore, you are going to have more reactants. The concentration of reactants will be higher than that of your products. Now, equilibrium is occurring in a closed system, but you can change it. You can disrupt it by changing the concentration of either the reactants or products, by changing the temperature that the system is at, or by changing the pressure. You can move the equilibrium point to get more product if you're trying to make something, which is where this all comes to be very practical. The scientist that figured out the effects that we can have on equilibrium was named Henri Le Chatelier, and so it is known as Le Chatelier's principle, that when we have a chemical system at equilibrium, we can stress it, and that stress will cause the system to try to create a new equilibrium. So how do each of these changes affect how the reaction proceeds once you put some stress on it at equilibrium? I'm going to start with a change in concentration. So the equilibrium constant is representing this ratio of concentration of your products to the reactants. And the ratio is just a fraction. So you know there are equivalent fractions. 1/2 is equivalent to 2/4. So because of that, if you change the concentration of reactants or products, the system will work to restore the ratio. It'll try to keep the proportions the same. So in this illustration I have over here with the graph, we have a system at equilibrium at this point. The lines have flattened out, and we see sort of this distance between the red line and the green line, and the green line and the blue line representing our reactants and products of the carbon dioxide turning into carbon monoxide and oxygen. If we add more carbon dioxide, we are changing the concentration of our reactant, which will cause a quick little blip here. It'll jump up. But eventually they will all even out again. We'll see equilibrium established at a slightly higher point so far as the actual concentrations, but the ratio remains the same. The proportion between these lines has returned to the same distance, and so the ratio is the same, just the concentrations have slightly changed. So it's kind of like a seesaw. If you add something to one side, the system wants to get in balance by changing the other side. So if you add a reactant, you will favor the forward reaction to make more product. If you add more product, you will favor the reverse reaction to make more reactant, to again get back into balance. And similarly, if you remove a reactant, your reverse reaction will be favored, again, to get back to that original balance, or if you remove product, you'll favor the forward reaction, which is where more practically we end up doing it when it comes to chemical industry. If we keep on removing the product from the system, the reaction keeps making more product. How about changes in temperature? Well, we know that all reactions are going to cause a change in enthalpy, a heat energy change, which is measured by temperature. And heat can be thought of as either a reactant in an endothermic reaction, it needs to go in, or a product in an exothermic reaction, it comes out of the reaction. So when you have a temperature that increases in your system, it's going to favor the reaction that absorbs the heat. So either whichever side, the forward or reverse reaction, whichever one is endothermic, it will be favored when the temperature increases because more heat is available to that reaction. There's more reactant if heat is considered a reactant. Similarly, a decrease in temperature will favor the reaction that releases heat because heat can move more quickly away from the reaction. It can move into the environment more quickly, it can get out of there, and so it favors that reaction. Changing the temperature will change the number that you calculate as the equilibrium constant because this temperature change has a continuous impact. So changing the concentration does not affect your equilibrium constant. You still end up with the same ratio of concentrations, but when you change the temperature, you actually do change the ratio between the amount of product and reactant at equilibrium. Here's just an illustration of what happens with heat with an endothermic reaction. We have dinitrogen tetraoxide, which is a solid. In this first illustration, it's inside the closed tube that you see here. And it's, of course, at very cold temperatures, well below 0 Celsius. When the temperature is increased, we're seeing a gas produced, and we're seeing a small amount of gas produced because it's kind of a light brown color. So in our problem, we see that our solid is now changing more to a liquid and a gas, and that gas, the the gas is giving the color. As we continue to increase the temperature, we see now we are pretty much left with liquid, or we've got gas all the way. We've got liquid in the bottom of this little container that's confusing me, but you're inside the tube, you've just got the two mixtures of the gases at a much higher proportion, and so you've got a much darker color. So instead of having a reaction that would just be containing, both the reversible reaction where you're going back and forth between the solid and the gas, we actually have moved all the way to the gas in this final point. And then finally, changes in pressure. Pressure is going to affect equilibrium reactions that involve gases. And so increasing the pressure in a system is going to favor the reaction which makes fewer moles of the gas so that the container can go back to the original pressure. So if the pressure inside the container, say, is 1 atmosphere and it is increased to 2 atmospheres, the reaction will move to pull molecules out of the empty space, the airspace there, so that the pressure of the reaction would go, or the pressure of the container would go down. The picture on the bottom might help you get an idea of how this works. We've got a container here on the left that has a certain amount of pressure in it. You can see how the particles are spaced out. They'll be running into the sides of the container at a certain rate as they randomly move around. If the pressure then is increased, they have less room to move. They'll have a higher pressure. They're kind of crowded. And so the reaction will be, the side of the reaction that will get rid of some of these particles will be favored because we've increased the pressure and now there's just like too many taking up space. The opposite is true. If you have a system that you decrease the pressure on, it will favor the reaction, either forward or reverse, that makes more moles of gas to, again, sort of fill things in. The second example here is going the other way. If you see, we've got arrow going to the left, and so we have a system at this level of pressure, and you can see about how close the particles are to each other. If you then decrease the pressure and spread them out, the reaction will try to fill in the spaces so that we'll have the same sort of arrangement, the same concentration, the number of particles in there creating the same pressure. Now, of course, not all reactions do establish an equilibrium, and we call those kinds of reactions ones that go to completion. There are several characteristics of reactions that go to completion. For one thing, they often don't happen in closed systems because some of the products can actually be removed. One of the ways that a product is removed is if it actually forms a solid and insoluble precipitate that falls out of solution, as we see in this first test tube over here. We have a precipitate being formed as we mix together two solutions, and so we can't move backward out of that solid. It's insoluble. It's not going to dissolve back into the liquid, and so the reaction is only going to go in one direction. Or if you don't have a closed system and you're making a gas that escapes the system, again, we have no way to kind of grab it and make things go in reverse. So our second test tube is showing a bit of magnesium and hydrochloric acid. You saw that reaction last week. And so this is, again, a reaction that goes to completion because one of the products is leaving. And if water is made as one of the products, it also will not reverse. And so these reactions are all called going to completion. They are not reversible. They are not going to establish an equilibrium. Why does this matter? Well, many of the reactions we use to make materials in chemical industry are reversible. So this is a very practical application of chemistry. We really are not making things in beakers, as we see at the left of this illustration, like we do in class. We're making things in these big industry with towers and pipes and all sorts of heavy construction. So these products are made in closed systems, and because of that, they'll reach equilibrium. And so by manipulating the concentration and the temperature and the pressure, the most product can be produced. And of course, when it comes to industry, that's what you want. You want to effectively produce the most product for those of us to use in our daily lives and to make profit, of course, for the industry. So hopefully this gives you a better understanding of equilibrium and why it matters and how we can change equilibrium by affecting some of the variables in and around the system.